started. So now I have to thank all my co-writers and co-workers. There's been a period of about 5 years trying to work with QCA and fuzzy sets and develop them. And my first thanks is to John McLaughlin, who's written some code in Python for today. And we've released that, and I'll give you the website where it's been released for others to just work with or have a look at or use. And then I also thank the British Academy, who funded this particular bit of research. It's not a huge grant, but it has allowed us to engage in Facebook and offer workshops on mixed methods. So we're continually trying to improve the way that statistics is embedded into mixed methods without dominating the epistemology of it. And you'll hear that today. COMPAS is a really good group of international scholars, and you can get the data sets that we use on the COMPAS website because it puts up nearly every data set that's had an article published about it. They're there for people to reanalyze and try replication. And finally, the GISMail Qual Compare email list, that's one that I run. And we don't have a lot of traffic on that list. We just have a query and then a quick answer, very, sophisticated, good answers that help answer queries on this tricky sort of set of methods. So I'm going to define what QCA is, first of all, and also what fuzzy sets are. So everyone should feel welcome. But I will move fairly quickly through the first part of the presentation and then come on to a definition of the measure of consistency for these particular ideas about causality. I'm going to focus on sufficiency in this talk, and then I'm going to talk about how to measure goodness of fit, which I think is a really exciting area. It's a growing area, which brings statistics to bear on the validity checks for the QCA findings. And you see here now in red my GitHub web address. So this is where John and I have put our jointly produced Python program, and it has a single line way to run that. So the command line, that's the instructions there. It's really short, and you just run it from the command line, and then it produces results for you, and you can vary the inputs to that really easily using a simple spreadsheet input. I do mean it's simple to alter your spreadsheet. So you could kind of do sensitivity checks of your own. Even just if you just want to use that to get the consistency measure, you can. And then, of course, if you're a writer, you could use that and write something in Stata that's similar. It's not that hard to do the QCA measures. So I'll give some findings near the end. My work isn't published yet with those findings, so there isn't a paper to refer you to, but I hope you'll enjoy the talk. So QCA stands for qualitative comparative analysis, and it includes fuzzy set analysis as part of it. And it's a set of systematic ways of studying causality. So we'd have to have a prior theory or some knowledge, at least based on literature review, in order to assert causality, and then have some measures, and then we would be able to apply QCA. And even from qualitative research, and especially international cross-comparative research, we would actually construct, as part of the data, a simplified data table. It might have a lot of binaries, that would be the crisp sets, or perhaps some ordinal variables, or variates, as Byrne calls them. I've brought one of Byrne's books with me and one of Reagan's. So this is Charles Reagan's 2008 book, which is very good. And Byrne and Reagan jointly edited a handbook on QCA and case-based methods. And Byrne says we shouldn't call them variables. They're variates, the things that vary across the cases in this group of cases. It doesn't have to be, associated with algebra. That's what he says. But I am associating it with algebra, so we're returning it to the usual frequentist discourse here. And see what works, what happens with that, get some feedback. So QCA helps you to discern necessary causality as well as sufficient causality, and there's such a difference between those two in QCA. It's been misunderstood by a number of critics who have assumed that we were looking for minimizing the errors of the line of best fit, and that's absolutely not what we're doing here. So I hope that by the graphic images in my slide set, that'll become more and more obvious. But I begin with something much more theoretical and qualitative. The way that Crescents, who wrote a seminal article using QCA in 2000, the way they describe it is they say it's conjunctural. It's about looking at the various ways in which the specified factors interact and combine with one another to yield particular outcomes. So how that cause happens is a sort of a verb. There's many verbs that one could use. It's not just a question of fact, it's a question of what is going on. And I think their article from the American Sociological Review is very good, American Journal of Sociology is a very good one. And I think the world's conjunctures are subject to change at lesser or greater speeds. Sometimes there's quite rapid change. So everything we say about the future from this is contingent, right? Things we say about the past are conjunctural, or they're about configurations pretty much in the past and the present. And at the bottom of the slide, you see the kind of words a sociologist uses to separate the social structure from the outcomes. I usually don't have a structural feature as an outcome. I could have a change in a structural feature as an outcome, but the fundamental social structure would be in the causes. The organization of the data for QCA involves a truth table, and I'm going to show you a couple of examples of those. Sometimes it's a table of all zeros and ones. Sometimes it involves fuzzy sets, which are between 0 and 1, including 0 and 1. And they measure the degree of membership in a set. So a set is then defined in words. It's an entity which we mean to refer to in society. So it works very well for economic or political concepts, not just for things like Likert scales. And one column is used. Can I show you an example then? This is an image of a data table, but here it's what we call an interim truth table. It's been summarized because there's a column for the number of cases. And the number of cases column says there's one case of the first type in row 1, but there's 4 cases of the next type in row 2. And this has been produced from a spreadsheet, basically. You can either do it manually, or there's freeware. So Charles Reagan has created free software. It's based in a website in Arizona that you can Google, and his is called FSQCA software. So I do recommend that. Later I'll put the name of that on the flip chart, because it's very important that we can use that. What I'm saying is consistent with that and complements it. So this paper in the American Journal of Sociology by Crescents, it has some data that we can look at. We can reanalyze it to illustrate the QCA. But it's really important to see, as ethnographers, they were not prepared to stick with one single outcome. They wanted to consider several different kinds of outcomes for the entities they looked at. Theirs were social movement organizations, especially orientated on homelessness. And there were only 15 cases in their study in USA. They weren't cities, they were organizations. So a couple of cities had 2 or 3 of these homeless organizations fighting for the rights for homeless. And R1, R2, R3, R4 in their paper refer to the 4 outcomes. So I think that's a good idea, because it allows some flexibility as you go through the research to model and change what you're looking at. So you might first look at outcome 1. I'll be calling it Y1. And then later on, have a close look at what's happening with R2. He called it R2. So he had rights and resources and 2 other things. They happened to start with R. But he was very careful to distinguish the outcome from the causes. And this diagram is basically an XY plot, with X on the horizontal as a cause and Y on the vertical as the outcome. Membership in the set of the cause X here is indicated X1 intersect X3. That means it must be the case that both X1 and X3 had occurred, which were defined as making a detailed prognosis of homelessness and the viability of the social movement organization. So it's quite a complex reasoning that has this combination or configuration on the horizontal axis. And then on the vertical, we have rights for homeless people, one of the outcomes. So this particular diagram illustrates necessity, and I'd like to show how that necessity pattern looks. X is necessary for Y if there are cases that empirically appeared here and at bottom right and top right, and there are none at top left. And it's actually a triangular shape, this necessity area. So the claim is that if the group of cases follows that pattern, then it suggests that X is necessary for Y, but doesn't necessarily cause Y, so it's not sufficient for Y. And we then can define another pattern as the pattern of sufficiency, which I'll come on to and illustrate in a little bit. It's quite well-known logic. I don't think this particular logic has really been questioned, but it's the confidence about saying that it's causal that some statisticians would question, because they'd say you haven't got a measure of goodness of fit of your model, and the traditional tests don't seem to work with that. But what Snow and Kress stressed, they wrote half their article purely in text form with an ethnographic exploration of unique outcomes. They said there's no single pathway for a single outcome. There's no universal causal pathway. It's a very beautiful qualitative article. It's institutional ethnography. And I do encourage qualitative people to use these methods. So in this paper, we're offering software which will measure the impact of X1 to X6 on any of the following Y1 or 2 or 3 or 4. And you just put your spreadsheet in and you get the results out. So ours now is called FSQCA. while Reagan's original freeware, which is very useful, is called FSQCA. These are complements and not substitutes. You just put your data in and you get graphs out. So now I come to the meat of my paper to explain how Eliasson and Stryker have offered us a statistical test. Now, I've been in touch with Stryker, and unfortunately, Eliasson has passed away, so we're unable to recover some of the data and materials that he used. But Ronghui Huang has actually coded the material. I'll just spell Huang for you, and he's living in China, but was at the time living in the same country as Eliasson and Stryker in USA. And their paper in Sociological Methods and Research offers an F-test. So I'd like to explain their F-test. I think it's a really valuable contribution that they made. And it's a test of the fit to a hypothesis that X is sufficient for Y. Now, they also offer one for necessity. And they also offer one for necessary and sufficient, which is very interesting. But I'm just going to take up sufficiency today so that it won't cause confusion. So can I now carefully distinguish necessary from sufficient cause and just explain that? So I've mentioned what necessity means in the sense of saying there is a pattern which ex post we might interpret as X being necessary for Y. But the sufficient pattern would be where in all cases where we have X, you get Y. So there's nothing in the bottom right corner. So I'll make reference a lot to the square of the fuzzy set vector space. Reagan calls it the fuzzy set vector space. So 0, 1, 0, 1, X and Y. And if there's nothing down here, then all the cases may be lying in this sufficient triangle, sufficiency triangle, where the data is consistent with that pattern. And I'm convinced by this so much. I'm prepared to argue, if you see the slide, you can practically remove the necessary cases, say X7 and X8, from your analysis when you're testing for sufficient causes. Because if they're necessary, they will be there when the sufficient causes operate. So the meaning I've stipulated for necessity is more universal across the whole group of our cases. So I hope that's convincing for you and helps you to see. We might return later to the idea of necessity within the sufficient pathway. And there's a term in philosophy called the INUS cause, where something is necessary as part of a sufficient pathway. So that can cause confusion, but I don't want it to. So here's our, it's the same data table, and it has some, X's which may be sufficient for Y, and others may be only necessary for Y. Is that clear? I hope so. So the test that Reagan suggested for measuring the sufficiency is a consistency measure. How consistent is the data with this claim? I think he ignores the issue of whether there's a random sample. And there's a huge debate in the journal Sociological Methodology debating this question and whether this is a valid conclusion. But Reagan says it doesn't matter if it's a sample or not, as long as the cases are real in the world, and this is a representation of them. I think we do need to know if it's a sample, to know which kind of test to use. And in fact, I brought with me a decision tree about bootstrapping. So if you were interested in bootstrapping, you might say, well, is there a random sample, yes or no? If so, then we could bootstrap that sample. And we offer pseudocode for that, because that's the next stage of our project. But let's just look here at sufficiency and the F-test for now, for today, right? Because that's hard enough. I found it a bit challenging. So for sufficiency, you're looking at the combination of some X's as well as each individual one. And you test every permutation, X1, X2, X3. And here in point 3, we're seeing the intersection of X1 and 2 and 3, which by saying and, or intersect, this symbol, we're meaning we take the minimum of those. Because if anyone is not present, then we're constrained and we don't have the combination of them. So that's the fuzzy set logic, and it's called Boolean Algebra. So this square is in the space of Boolean Algebra, but later I'm going to move to a new space, which is Euclidean Algebra, and that, it's just on a different scale, and different algebra, different sort of techniques. And this is the advice given by Eliasson, which I really like. But let me stop and just give you the traditional measure of consistency. It's a ratio defined as the sum of, for all the cases, the sum of X intersect Y. So it's saying to what extent is it the case that Y exceeds X, because there's a special feature of this sufficiency triangle. In this triangle, in the representation, and Steph will talk about calibration a little, when we get to this, it is the case that Y exceeds X for every case, if all the cases are in that triangle. Y is greater than X. And here, when we take the sum and we intersect them, then we're looking at to what extent is it the case that that's true, right? So then we divide that by the sum of all the x's. So what happens is, for any point that lies below the line, I'm just going to draw one here, and there's some images in the slides in a moment. For any point like that, you get a reduction of the numerator, but you still add 1 unit to the denominator. So it goes less than 1. So consistency should be 1 if X is sufficient for Y, that all the cases lie in that sufficiency triangle. And it would be, say, 0.9 here, if cases are here, 0.8, 0.7, and it's going towards 0 as they move outward. It doesn't move in a linear way. I'm not going to draw a picture of it for that reason, but that is the fact about consistency. So here's my slide, just illustrating the sufficiency triangle and the necessity triangle, and points along the line could count toward either. So that's what Reagan's books are about. He's a wonderful author. He's written a number of really good books. And point A, according to his logic, wouldn't really, it's just consistent, right? A single case at point A is consistent. B is not consistent. But the amount that it reduces the consistency measure by depends on the distance from B to the diagonal. So that vertical distance upward after the point B. And C, actually, if you have cases at the bottom right side, it adds a huge amount, and thus it reduces the consistency measure. So Reagan suggests that C is very important, and that we should have a cutoff for C. He suggests it should be 0.8, or in this book, around page 139, he suggests 0.75. So it doesn't have to actually be 1. You could have some cases, or a few erratic cases, or 1 or 2, or small errors on all cases, and they might deviate. And that's been really controversial. How much would they be allowed to deviate before we would have to accept that X wasn't sufficient for Y? So that's the question we want to address. Here's an example. Here we have data from the references just on the next slide. Freitag and Schlicht in 2009, Educational Federalism in Germany. And in this slide, the bulk of the data sets, data points, which are regions of Germany, they lie in the upper left triangle. There are 5 that are deviants. So, do we get a measure that's below the 0.8 cutoff? Should we use the 0.75 cutoff? We can debate about that. I think Patricio Francosa Ruiz, who's helped me to just have this data handy, you can either go to our GitHub area or go to the Compass website to get Freitag and Schlicht's data, because they're quite useful fuzzy sets based on aggregates for schools. And the question here was, what would be the cause of social inequality? Was it rooted in schooling? And the specific X that's being measured here is the low availability of early childhood education. We've swapped it round to be low to get evidence for the sufficiency hypothesis. And this swapping is common, that we would actually look at converses, right? The converse of Y. So you do the test for whether the X causes Y, but then you also do a series of tests for whether there are causes in the data for not Y, and that is not symmetric with the results for Y. So the protocol is a bit time-consuming to do a series of tests. So I've brought a couple of copies of my training materials. We have a summer school at Manchester, and from the summer school, the protocol is actually in this handout. So if there's some of you who want to just have a copy of that, you can. Protocol taking about a page of steps, just to make sure you cover everything. And this is how it looks when it's done. But the results in our software, it's the same. Can you see that that's the same pattern? There's 5 exceptions to the rule there, 1, 2, 3, 4, 5, and the others lying there. We've just changed the scaling, and there's the original data as well on this slide. So later education is somehow associated with social inequality being higher. That is the absence of early education for children in Germany in the years preceding 2009. So for them, they got consistency 0.876, and that certainly meets the cutoff. It certainly looks triangular. And one proposition in the literature is to do a quantile regression on the data. But you'd have to, you could find the pattern that way, but then you'd have to run that on every configuration, and nobody's bothered to do that. But it is certainly one way of getting that pattern for where there's a gap, there's a big space in the vector space. So now can I introduce the DSUF measure, the Eliason and Stryker measure? It's not original with me. Reagan had suggested softening the CSUF. So I think Eliasson and Stryker and I are all responding to the need to have something that gives us more of a guideline and more of a language to talk about softening this. So we'll try frequentist discourse. Frequentist discourse is when we either say there's sampling, so I've got my bootstrapping for sampling, or we say there's measurement error. And those are two completely different things. We may have both. So Eliasson said if there's measurement error, then we can probabilistically say what patterns in the population would have a chance of satisfying our expectation, our null hypothesis. So I'm going to frame the null hypothesis in a moment, and that is definitely frequentist. But my argument is, in a deep way, we can combine frequentism with realism. So, critical realism, there's no problem. We could do multi-level modeling in the same way. So what Stryker and Eliasson said was, let's allow measurement error to move the consistency cutoff line outward a little. If we're testing for sufficiency, we'll move it down a little. If we were testing for necessity, we'd be moving it up a little. And they suggest that we should have that bending. So I leave that for you to think about. I'm just going to have a constant measurement error. What they described was that the measurement error might be greater in the middle of the vector space and less at the edges. And there were different reasons for that. Just convenience, really. So we say for the error on the vertical axis, we'll have epsilon. And they then say epsilon has to be uncorrelated with y and x and eta. So if it's uncorrelated, the statistics simplify a lot. And I'm going to show you that in a moment. Then they show that to add up these distances, the vertical distance from a point to the diagonal, you can just square the distance between x and y. So x minus y squared is a magic number in the D stuff. And you can use Stata. We've used Python software. You can use R or even SPSS or even Excel to calculate this. But if you have 5 conditions, you're going to have about 63, that's 2 to the k minus 1 configurations. So if it was Excel, you'd have to have 63 worksheets, each with your results. And that might not be very convenient. So we've used Python to just run through that in loops. If you know looping in Stata, it's easy to write this in Stata. And we use the number D to represent whether a point is in the upper or the lower triangle. If it's in the upper one, we'll have D equals 1, lower one, D equals 0. And what we do then is multiply x minus y squared times 1 minus D. So when D is 1, we don't get anything added to the distance measure. So D is a distance measure. We'll call it D suf. It's very similar to C suf. It's related, really. But it's in a different vector space. We're now in a Euclidean space, and I need to explain about that. So I've just illustrated here how you can transform your fuzzy sets into a Z variable. So a Z transformation is subtract the mean and divide by standard deviation. But what Eliasson and Stryker did was a little different. They said take the inverse cumulative normal of the value. So if this value is between 0 and 1, find out which Z value corresponds to that as a probability. And that's really clever because for 0.5, it gives you the number 0. And for 1, it gives you infinity, 0. So he said we have to dampen the edges of the original fuzzy set box. Just dampen them very slightly. Thank you. And when you've done that, you won't get infinity. And so now I can mimic the shape of the data. Can you see that these points exactly mimic the ones in the fuzzy set vector square? I now get them in a Euclidean space where measurements, like distances between things, can be measured using Pythagoras, etc. So these tricks are in Stryker. Trick 1, convert to normal distribution scores in a special way. The inverse cumulative normal distribution. And trick 2, measure the distance from a case to the diagonal line, and they use x minus y squared or y minus x squared. It doesn't matter which one you use. And that turns out to be a really helpful part. So the formula now in our program is if d equals 1, then add to the distance measure the distance x minus y squared. And I'll say zx and zy for these transformed variables that are in the z-score space. Just to remind you then, the axes have the numbers from about -3 to +3 on the horizontal, and from -3 to +3 on the vertical. And so the diagonal's going through the 0, 0 point. So that's how it's set up, and here's a summary now. So what Eliasson said was, he actually said we should name this the Sheldon-Stryker F-test, but it's just an F-test. An F-test typically in regression works this way. Remember how you have the variance explained divided by the variance that would exist if the variables were random? And we find that in ANOVA as well. And if the numerator is bigger, you get a larger F. And if the f is larger, you get a p-value that's smaller. So you reject your null hypothesis. That's the way it works. So he developed this f-test, the empirical distance d sub, divided by what we would have expected if all the points were in the upper triangle, and with the measurement error. Because if you didn't have the measurement error, then the denominator is 0. And that's no good. It drops, it just becomes non-existent. So with the measurement error, he actually is able to evolve an f-test. So I'm just going to show you then how we can explore the sufficiency testing. The mean, it's quite interesting to think about the mean of x and y, because as that moves up, you're tending to end up with a high level of consistency, right? And as it moves down, not necessarily so, it depends where it is, but to some extent. And actually, the mean of x and y appears implicitly in the numerator of the consistency measure, and it appears implicitly in our d stuff. So we do have things that move in different directions. So c stuff goes up and should be between 0.8 and 1, but d stuff should go down if the data is consistent with sufficiency, and it should be small, and sometimes is just 0. So we can put a confidence interval around this d stuff. You don't even need the f-test if you do bootstrapping. But I'm not going to talk about bootstrapping today. The f-test, on the other hand, needs quite a lot of unpicking. So I've got the formula on slide 29, and I still have to go through a bit of empirical results. So I'll mention this formula, and we can take questions later on, or by email. So it's the ratio of the sum of squared distances divided by what would have been expected as the sum of squared distances, just taking those error terms. And the argument in both Eliason and Huang is that the denominator is just the sum of epsilon squared. The expectation of epsilon squared. So we can put a scalar parameter in, and then it'll give us a sort of, an innocuous denominator. But the real action is in d sub, and then you divide it by the degrees of freedom number 1, and the f-test, I've got a copy of it here on 2 pages. It's a test with 2 degrees of freedom, the first versus the second, the numerator versus the denominator. And the numerator degrees of freedom goes in the top. And that's actually the number of points like this green one that are not consistent with the hypothesis. So we've got a spreadsheet coming out of our package. I'm just going to skip to that spreadsheet for a moment. The spreadsheet actually shows the df1, the f, the p-value, the c sub, and the d sub. That's the output from our program. So that's around slide 40. So just going back, apologies. So these are the formulas that sort of put it all into order, how we add up the sum of squared distances, divide by df1, and how we put that epsilon squared expectation in the denominator. So there's not much time really to go into all the detail at the moment, but it is consistent with Eliason's paper. It's not a change in it. And if f is large, there's a lack of support for the null hypothesis. So we want f to be small. And whereas, if it's consistent. And so when f is large and p becomes small, then we have a significant finding. We reject the null hypothesis. So we're actually trying to falsify our own claim that x is sufficient for y. So when you've done your f-test, if you haven't rejected it, you have not proved it, and you shouldn't accept the hypothesis either. But you're just saying, we tried to falsify it, and we couldn't. And we'll go ahead and work with that. So I hope you might like that language. I'm not sure if you will. We do run into some issues. So when consistency is 1, this all drops away because all the points are up in here. There's no distance, so there's no f. We don't really need it. And that'll have implications for if you try to computerize it too much. But what people usually do, when they've run the program and they've got the 2 results, they usually then, so I've just put that GitHub address there where the program is. You can download it. And you look at all your graphs. We're producing these graphs for you so that you can really see each configuration plotted against each y. Then usually we start to examine the results and think, well, what is really key among all the configurations? So there's a Boolean reduction that we usually do. Now I'm just going to check in this audience, how many are familiar with Boolean anything or Boolean reduction? Just indicate for me. Okay, so some of you have been exposed to it. I put the rules here for it just to illustrate. So if you often have A and B associated with Y, and cases of A and not B, then you can practically drop away the B, because B could be either there or not there. It doesn't seem to matter for Y. So in the reduction process, in FSQCA software, it drops out. And you can do that manually. Once you've got your FSQCA results, you can just sit and just manually go through those. So I encourage you to think about the reduction and the commutative rules that may apply, the problem of symmetry, really, really work your way through that. Because looking at my example, I've got a p-value of 3%. Now 3% means would you accept or reject if significance in the sense of the p-value was 3%? You'd reject, right? But in the same cases where it's 3% here, and this is slide 42, the consistency level is very high. It's well over 0.9.